I will be presenting on some ongoing and planned work that we're organizing out of Scripps, but as it says here, I'm currently working on a Fulbright fellowship at the University of Grenoble-Alpes. So part of this talk will be on their behalf. That's how we'll start. And everything I'm going to talk about, nothing of it would be possible without a lot of support, including a grant from the NSF, another grant from NASA, and then a tremendous amount of support from around the world. So this work also wouldn't be possible without these two wonderful people. Tyler Pelly is a Green Foundation postdoctoral fellow at Scripps. Been there for about the last year, recent PhD graduate from Matthew's group. He does coupled numerical ice sheet and ocean modeling in East and West Antarctica. And then incoming PhD student Briar Conger, who will be working on geophysical investigations of subglacial hydrology coming out of Dusty's group at Stanford. Okay, so the three objectives of this talk. Number one is to convey the status of field activities in the French Antarctic program. And then number two, we'll look at a radar survey that was done in 2018-2019. And then the third thing is to focus on the ocean sensor deployments that Wan Song just mentioned in his presentation. Okay, so first, unfortunately, Catherine Ritz and Manu Lemire were not able to attend, so if they're online, hello. And so the following slides are on their behalf, and their email addresses are down here, so please feel free to reach out to them. So they wanted to emphasize that collaborations are very welcome. They are very enthusiastic to collaborate on things like what will happen, projects that will come from this workshop. IPEV has a very long history of supporting such projects out of the Cap Prud'homme station, which is the joint Italian and French base, and the D10 skiway, which is very close to Dumont-Deville station. But they did want me also to point out that France does not operate aircraft or instruments that RINGS probably will need, and is not currently in a position to mount its own program, which is why they wanted to emphasize this history of collaboration. They also wanted to point out that IPEV is in a time of transition with some issues they're just working through, like staff shortages, renovation plans, and that may lead to some berth and storage shortages in the next few seasons. So unfortunately, they're not accepting new logistical plans until the 24-25 field season. But anyway, with that knowledge, please reach out to them and with ideas. I'm not going to read all of this, but it's in the recording. There's also some references down here for more information about these projects. But what I wanted to highlight here are there are four ongoing French programs that are complementary to RINGS. So when you think about collaborating with the program, keep these projects in mind as well. And then the next few slides will emphasize these two, sort of a marriage of the Glacial Clim project led by Vincent Fervier, and then the Ice Cap George V surveys that Dr. Chui and Duncan have mentioned earlier today. And so that's what we're going to focus on here. So now bringing it into RINGS, this cartoon was inspired by our discussion that Kirsty and Ryan led yesterday. The outer ring, which I consider the primary ring, has a lot of necessary processes, including surface processes. And so what we're going to look at here is how we can use airborne radar to study some of those processes. And I want to call out Cyril Grima, who's at the University of Texas Institute for Geophysics. He developed he's a radar scientist, also educated in Grenoble, but he developed a technique that has been applied all over this planet and Mars, and is going to the moon soon, to look at surface properties from using a backscatter model. So basically, inverting for surface roughness and permittivity from a backscatter model. And so what you're seeing here is a paper from 2014 where he estimated the surface density from the permittivity all over the Thwaites Glacier catchment. And he used data from Brooke Medley's 2013 paper to show that there's this correlation between surface density derived by the airborne radar and accumulation. So the data set that we collected in the 2018-19 season that Dr. Chui referred to earlier today had a lot of data, and I want to highlight a few things. You know, the emphasis was the coast, but we also visited John Bogo Station and Mario Zucchelli Station's runway to do a survey for old ice at Elephant Moraine, which was used to calibrate this technique so that we could apply it to the Asuma Traverse, which was a French project called Improving the Accuracy of Surface Mass Balance in Antarctica, led by Vincent. So this is a very interesting, this is kind of a micro rings sort of thing, where we had multiple programs working together with different aims and interdisciplinary ideas. And this is the result. So combining the data that Vincent collected along the Traverse, which was 18 density measurements, with Cyril's surface density calculation from the radar data, we get this sort of very unique data set to see how accurate this density product is. So these are the 18 points, these are the statistics, and long story short is that the radar does a really good job at not only matching the sort of trend of the data, but also the absolute values are pretty close. There's a few of these points that the Asuma team, in this case, in this location, did 3 different measurements, and like this one doesn't agree with the radar, but these two do pretty well. As well as here, these two didn't really agree, but this one agreed pretty well. So there's scatter in both data sets, but overall the answer looks really good. One thing I want to highlight here too is that this Cyril's technique can be applied to any airborne radar. It doesn't have to be the HICAR system. And if you have the accumulation radar also, then you can look at things like, is this density, is this snow due to wind-blown snow or accumulation, right? You can back that out if you have a density calculation and an accumulation calculation. So with my remaining 3 minutes, I want to jump into the ocean sensor part of the talk. And basically we're focusing on several key areas where there's a lot of mass loss. We're using these sensors that you deploy out of aircraft. The sensor goes in the water, a probe descends to the seafloor, and there's a UHF link to the aircraft. Yoshihiro Nakayama has a paper that's just been accepted in GRL using the data here, and you can see basically the bottom. This is the bottom strike, and this is the bottom temperature. And if you combine this with gravity data, you can constrain your inversion a bit in areas where ships haven't been able to access. Plans for the coming seasons with the Australian Antarctic Division include the Denman-Shackleton area, where we're trying to fill in areas with no gravity data and then deploy grids of those sensors in sea ice leads. A similar story for the Cook Ice Shelf region, grids and gravity. And then in the next few slides, I'm going to highlight these data, but with the Korea Polar Research Institute, we figured out how to deploy sensors in the Thwaites Rift. And so something we started talking about is returning and deploying a Hui ice tethered profiler that Scripps owns in one of these areas where the fast ice is stable between icebergs. And so now with my remaining minute and a half, I'm going to just follow up on, pick up where Wansan left off on the airborne deployments. As I just mentioned, we deployed several sensors. Some of them were pretty easy because there was open water obvious in the satellite images. But as we got closer to the grounding line, the targets were covered in ice, and they were really small. So thanks to quick thinking by David Holland and Scott Polfrey from BASS, really have to highlight their contribution, and our colleagues from COPRI who helped with every part of this. We were able to come up with a new technique for deploying these sensors. So this is an example between icebergs about 4 kilometers from the grounding line, where we found this sort of gray section, about the size of this part of the room, covered in ice. So what we did is we removed the sensor, we filled the case with mooring shackles, thus was born the Shackleton bomb, deployed the Shackleton bomb to break the ice, and then using spools that Scott, that I just mentioned, Scott Polfrey designed for each probe, we lowered it carefully into the new hole, and then got these measurements. So the main thing the take home here is that the Gaddy mixing line, as defined by the profile that was acquired out here, plots really nicely along the profiles that were collected near the grounding zone. And these two profiles are fun to compare. This is sort of that inflow profile that looks like a typical, CDW intrusion profile. And this profile is where Sushil Adusumilli showed 80 meters per year of melting going on between 2010 and 2018. And when you look at that profile, you can see how much warmer it is in the upper 400 meters. It's cooler in the lower layers, but you can see as that, the buoyant melting has, raised up that deeper warm water into that upper layer. And so that, just to highlight here, where that melt's going on, that's where, this is from the bed machine compilation, the bottom of the ice is at about that depth. So, so we're seeing all that heat go right to where those icebergs are. Also, for Tom Jordan, these are the bottom strikes compared to your gravity inversion, and they plot really well. The black line, then the gray line was from before. So this is a nice way of, testing those inversions. That's the end of my talk. Sorry for going a little long, but just want to acknowledge our supporters in this work. So thanks for having me.